Welcome to qnawire.
In this question, we propose this following photon decay, and this decay actually violates a lot of conservation rules, so this does not actually exist. But we assume this exists, and then we assume that proton has a half-life of 10 to the 18 years. So part A, we want to calculate the energy deposited per kilogram of body tissue in RAD, Ng in RAD, due to the decay of protons. So we also want to, it also gives us some of the information about how we can model a body. So the very first thing we should do is we should know how many protons are there in a kilogram. So for each kilogram, we can first multiply it by Avogadro's constant, 10 to the 23 molecules per mole, and then 1 mole is 18.0 times 10 to the negative 3 kilogram per mole. We're assuming our body is purely made up of water. And then we have 2 protons per molecule. So we have 6.7 times 10 to the 25 protons in each kilogram. And then we know that each proton has the amount of energy, MPC squared, is 938.3 MeV. And if we convert it into joule, it's 1.5 times 10 to the negative 10 joule. So given this amount of information, the energy deposit in a year per kilogram is going to be the number of protons times in a year, we have 2 over 0 times 10 to the 18 years. This is a lambda we have, and let's remind you that dn over dt equals lambda n, and we're using this equation right now. And we know ln 2 over the half-life is going to tell us what lambda is. Now the time is a year, and the amount of energy is 10 to the negative 10 joule. So this gives us a dose of 10 to the 7 times 10 to the negative 3 gy, which is 0.7 rad. And then in part D, we want to find the equivalent of the equivalent dose. But we have an RBE of 1, so the equivalent dose really, it's still 0.7. Its equivalent dose is going to be 0.70 REM.